Hello, my name is Matt Genge and I'm a scientist at Imperial College in London. And I'm here today to talk to you about climate change, in particular climate change in the Earth's past, because over our planet's long lifetime, climate has changed continually. And so what I'd like to do today is look at just how different the situation is today, how the change that we are producing is something unusual even in Earth history. Now, I should say that I am a geologist who studies the Earth's past and a planetary scientist who studies other planets and asteroids and comets. So I am not a climate scientist. So I do not receive money for research to do climate science. So I am an independent scientist. And really the point is to show you that the vast majority of scientists in the world, regardless of their background, agree on the causes of climate change.
One of the difficulties about observing climate change is its timescale. So we have relatively short lifetimes. If we compare our lifetimes to the age of the Earth, we are living virtually in an instant of time. So our planet is 4.5 billion years old. And that makes it very difficult for us to see changes happening. And in fact, for a long time, with climate change, nobody noticed that the climate was changing. It was just too slow. And yet today, what's remarkable is that all of us are starting to notice that there are things about the climate which are different. There are more extreme weather events. There are hotter summers. And that's truly worrying, because this is a pace of climate change which has very, very rarely been seen on Earth. So let's ask that first question. Is climate change actually happening?
So here is the best evidence that climate change is actually happening. Because obviously we can measure the temperature of the air that surrounds us. And if we do enough of those measurements, we can obtain a global average temperature. And this shows those average temperatures back to about 1830. And you can see at first the temperature, the average temperature, is fluctuating. And that's a natural process. The sun goes through phases of activity roughly every 11 years that affect global temperature. But look what happens in about 1910. The temperature starts climbing upwards and continues all the way through the 20th century, apart from this little period between about 1940 and about 1970, where the temperature is more or less flat. Now, to a scientist, this evidence is really convincing. You might notice the little vertical lines on these data points. These are error bars, and errors are not a bad thing. Errors tell us how certain we can be. And notice the error bars have got smaller and smaller as we've been able to measure that average global temperature more and more accurately. So temperature really is increasing. Now, it was, for some reason, flat between about 1940 and 1970, but that was a period when there was a real effort to clean up global pollution, and that affects climate. There was also a big eruption in 1963. So there are reasons why there was no climate change occurring, or no increase in temperature occurring during that period of time. But what's really dramatic is the amount that global temperature has gone up compared to this natural variation in temperature. So climate change really is happening. This to me is one of the most convincing demonstrations that climate change is really occurring. So this shows global temperature each month for every year through the 20th century to today. It demonstrates that the 20 warmest years have been in the last 22 years. Now that's something that we have all noticed with our own eyes. it has now become impossible to deny that climate change is occurring, to deny that global temperatures are increasing. So let's look from a scientist's point of view, an independent scientist, of why global temperature is increasing. And looking at this data here, I can see that the CO2 concentration in the atmosphere, which is something we can measure that CO2 concentration, has increased throughout the 20th century and is continuing to increase today. Now, we know that CO2 is a greenhouse gas. Now, later in this talk, we'll talk about the Earth's past, and we'll see that CO2 in the Earth's past also has a similar effect of increasing global temperature. So the increase in CO2 concentration of this greenhouse gas in the atmosphere, especially since 1970 onwards, is associated with a rapid increase in global temperature. So let's look at why those greenhouse gases act in the way they do, because that's quite important to understand, because it really demonstrates how this has to be the cause of global warming. So it's quite easy to understand why some gases cause the atmosphere to heat up. And it's a process called the greenhouse effect. It's actually not much like a greenhouse, but it's similar. And it's pretty easy to understand. So we know that when sunlight comes through the atmosphere and hits the ground, it starts heating up the ground. And as the ground gets hot, it starts releasing that energy again as heat, as infrared radiation. Now, you're all familiar with this effect. If you've ever been on a beach during the summer and you felt the heat coming up from the sand, that radiation coming up from the sand, then you know that hot things release heat. They release this infrared radiation. And of course, that heat comes up off the ground and is trying to escape back into space, allowing the Earth to cool. And that's where the greenhouse gases come in. Now, to do this, I need an atom to demonstrate it. I've got an atom, it's a very big atom. I need two really, so unfortunately, I don't have a second one. So this coffee cup is also an atom. And it just so happens that some molecules, that when they vibrate, when the atoms vibrate backwards and forwards, they do so at the same frequency as infrared radiation. And that means they can absorb it. So these particular molecules absorb heat, which makes them vibrate even more. And then that vibration decays and they release that radiation again, still as infrared. The reason that that's important was that the radiation, the infrared radiation that was escaping from the Earth, when it's re-emitted by these molecules, when it's released, it can be traveling upwards and still escape, or it can be traveling downwards and reach the ground again. So essentially that radiation is fired back down towards the Earth's surface. That heat is kept in the atmosphere instead of escaping back into space. And that's the reason that greenhouse gases make our atmosphere warm. And we should be very pleased that they do, because if they didn't, our planet would be uninhabitable. It would be frozen. It's the global warming effect that ensures that our planet is a good place to live. And it's not just CO2 in the atmosphere that absorbs this radiation. It's also molecules like water and methane. So global warming is a natural process, and it's all to do with the behavior and the vibration of molecules. And thus it's an inescapable effect. It has to happen. And so we know that the increase in abundance of a greenhouse gas like CO2 is bound to increase the amount of heat kept in the atmosphere. There's no way to avoid it. So the fact that we see CO2 concentration increasing gives us the most likely explanation for climate change for the increase in temperature that we observe. So we can see that global temperatures have to increase if you increase the amount of greenhouse gas in the atmosphere. It's a natural process, it's unavoidable. And so really the cause of climate change is whatever is producing that gas. So we can ask the question, is it volcanoes? Is it a natural process that's producing that CO2? Or is it our industry and our land use? And the figures actually speak for themselves. So we can measure the amount of CO2 that's released by volcanoes around the world, and we can calculate how much gas is produced by volcanoes. Now, there will be some error in that calculation, some uncertainty. But if the numbers are big enough, if there's a big enough difference, we'll know what's responsible. So the amount of CO2 produced by volcanoes worldwide, and we're pretty confident about this number, is 200 million tons of CO2 per year. 200 million. That's a lot of CO2 being produced by volcanoes. The amount of CO2 produced by industry and our land use and everything we human beings do is 37 billion tons of CO2 per year. That's 185 times more than all the volcanoes on Earth at the present time. It's undeniable that the amount of CO2 in the atmosphere is the result of human beings, and that the amount of CO2 is causing climate change. You really cannot avoid that conclusion. So the climate's definitely changing. And this isn't the first time in Earth history that our climate has changed. It has changed many times in the past. And some people suggested that we don't really need to take any drastic action because the Earth will recover from climate change. Some people have even suggested that what's happening now, us producing CO2, is somehow protecting us from an ice age. Maybe climate change is a good thing. So let's have a look at some of these questions by looking at what's happened in the Earth's past. So there have been many glaciations in Earth history, and in particularly in the fairly recent geological history, there's been quite a few. So there have been 8 glaciations in the last 800,000 years. In fact, the last one ended only 11,000 years ago, and that's virtually yesterday in terms of Earth history. So actually, this suggestion that the CO2 we produce might be staving off a glaciation, it sounds plausible. And in fact, when we look at the Earth's past, when we look at these glaciations, we can make measurements on them because there is still some ice around that formed at the time of those glaciations. And we can analyze little pockets of air trapped in that ice and measure the CO2. And what we see is, yes, indeed, during interglacial periods, there is more CO2 in the atmosphere than during the glaciations. And yet, it's always less than the amount of CO2 that's in the atmosphere right now. So we're now at around 410 parts per million. That's exceeded the records for the entire 800,000 years before this. So let's have a quick look at how you can measure temperature in the past, because obviously that's important. How do we measure the temperature of the Earth's atmosphere? So measuring past temperature is a little bit tricky because, of course, you can't send a thermometer back in time just to see what the temperature was. So we need to use other methods, and I just wanted to explain really how reliable those methods are. And again, I'm going to use my little atom. So one of the ways we do it is by measuring the abundance of isotopes. And I'm going to need my atom, and I'm going to need a box. So, for example, we can measure the abundance of an isotope called deuterium. And deuterium is heavy hydrogen. So it has about twice the mass of a hydrogen atom. And it fits quite well within ice. And what controls how much deuterium fits in ice depends on how much deuterium can fit in the holes in the ice structure. And the problem for deuterium and hydrogen is that these two atoms are constantly vibrating backwards and forwards. At any temperature, atoms vibrate. And the heavier the atom is, the less it vibrates at that temperature. So for deuterium, which is heavier than hydrogen, the colder the temperature, the less deuterium vibrates, and the more likely it is to fit in the hole in the atomic structure of ice. So the amount of deuterium within ice increases the colder it gets. And we can use experiments and calculations to work out the temperature from the amount of deuterium within the ice, simply because atoms vibrate more at higher temperatures than at low temperatures, and that affects how much you can fit inside a material. So one of the really interesting things about glaciations is just how many of them have occurred, and they're more or less equally spaced, so it looks like some kind of cycle. And we think that they are produced by changes in the Earth's orbit that mean that sometimes there is less sunlight, less heat arriving at the Earth, causing global cooling. And these are known as the Milankovitch cycles. And one of them, for example, is where the Earth's orbit changes from a circle into a slightly more elongate shape. And that's known as eccentricity, and that occurs once every 100,000 years. There's actually three cycles. There's one where the Earth's rotational axis changes angle every 41,000 years, and one where its precession changes, and that's every 23,000 years. And the sum total of these different wobbles produces changes in the amount of heat arriving at Earth that can cause global cooling. So if that's the case, why do we see more CO2 during interglacials than we see during glacial periods? If it's not the CO2 producing that's driving the change in climate, why does it change at all? And the answer is that the climate is a very complex system, and that CO2 and temperature are interdependent. We say that there is a feedback between the two, and it's those feedbacks that make climate so complex. So we're all familiar with feedbacks. Now, if you've ever taken a microphone a bit too close to a speaker and heard it squeal, you'll be familiar with a positive feedback. The speaker produces more sound, which is recorded by the microphone, which transmits more of a signal to the speaker, which produces even more sound until the thing really begins to squeal. But the climate and CO2 is a much more complex feedback system than just a microphone and a speaker. And so we need to look at some of the feedbacks that can control climate, because they're really the key. Really good example of a climate feedback is produced by ice. Now, as anyone knows who's been out in the snow is very bright. It reflects a lot of sunlight. And so during the glaciations, when a lot of the Earth's surface is covered by ice and snow, it reflects a lot more sunlight back into space, and that causes further cooling. In fact, if it wasn't for greenhouse gases, then glaciations would run away and we'd have a snowball Earth with global glaciations. So climate feedbacks are critically important in moderating the Earth's climate, and some of those involve CO2. So we probably all know that plants absorb CO2. During the day, they take in CO2, which they use to grow, and they release oxygen through respiration. And the more plants there are on Earth, for example, during the warmer periods, then the more CO2 can be drawn down into plants and fixed on the surface. So during the glaciations, when lots of the Earth's surface is covered by snow and ice, there are less plants and less CO2 being absorbed by plants, partially balancing the extra reflected light coming from snow and ice. So an example of a climate feedback involving CO2. One of the most important climate feedbacks is provided by the oceans, simply because you can dissolve CO2 in seawater. And so the oceans are constantly absorbing CO2 from the atmosphere. If the amount of carbon dioxide in the atmosphere increases, then the amount absorbed into the oceans also increases. So the oceans help control the Earth's atmosphere. They help control the climate. And what's important is that at lower temperatures, for example, during glaciations, seawater absorbs more CO2. In fact, you've seen this yourself. If you've ever looked inside a kettle and seen limescale, that limescale represents the CO2 that's released as that water is heated. So the oceans help control the abundance of CO2 in the Earth's atmosphere. And that's absolutely crucial in controlling the Earth's climate. Glaciations also significantly affected the sea level on Earth. So during the last glaciation, sea level was a full 120 meters lower than it is today. So the whole of the North Sea between the UK and the rest of Europe was land during the last glaciation. The English Channel between France and the UK was also land. And I've got some dramatic evidence to demonstrate this. So covering the bottom of the North Sea are things like this. This is a mammoth's tooth. And it was dredged up from the bottom of the North Sea. So there were mammoths wandering around what was then land and is now the bottom of the North Sea. In fact, at the end of the last glaciation, there are features at the bottom of the English Channel suggesting that the English Channel was carved by some great floods of water, by a large lake that accumulated in the North Sea, and that it was carved in a couple of large floods. So sea level changes dramatically when you melt ice. And of course, that's a concern now because glaciers and ice caps around the world are melting because of increased temperature. So there are really good measurements of sea level, including historical measurements. And they tell us that sea level has increased by 23 centimeters since 1880. That's a huge amount of increase over a very short period of time. And current measurements suggest the rate of change has increased. That we're now at 3.3 millimeters per year. Now that might not sound much, but it's a huge problem if you live by the sea. So the predictions are that by 2100, sea level could rise by a further 26 centimeters to 77 centimeters. That level of change will cause major flooding of coastal communities and coastal cities. The maximum that could of sea level rise that could be produced is if we melt all ice and temperature continues to increase so that we get thermal expansions of the oceans. And so if we melted all ice on Earth, global sea level would rise by 65 meters. 65 meters. Now that's not going to happen. We're very unlikely to melt all ice on Earth. But when we look back in geology, we see periods of the Earth's history when that did happen. During the Cretaceous, there were very small or perhaps no ice caps, and covering most of the Earth was a shallow sea with relatively little land. It has happened in the Earth's past. It is in the process of happening now. So what about the claim that climate change might be a good thing, that the CO2 that we produce, increasing temperatures, is staving off another glaciation? Well, because we know what causes glaciations, it's the wobbles in the Earth orbit, and because we know that that we can predict those wobbles. We can predict when the next glaciation should be, when there's the least light coming to Earth. And predictions are that it's in about 50,000 years' time, and that we are just over the peak of an interglacial right now. So no, CO2 in the atmosphere is not staving off another glaciation. We have to wait another 50,000 years for that glaciation. All it's doing is increasing global temperature and causing sea level rise. So we've talked about those periods of Earth history when the climate was a lot cooler than it is now, the glaciations. So let's have a look at some of those times when the climate was a lot warmer, to make a comparison to what's happening now. Just what was the environment like on Earth during these hot periods? One of them was during the Cretaceous period, and it's thought to have been caused by a greenhouse effect, by large amounts of CO2 being produced by volcanoes. And there were many more volcanoes present at the time because there was a supercontinent called Pangaea that started to break up, and that involves the formation of new oceans. And when oceans form, they're created by a line of volcanoes that run down the middle of the ocean. So these volcanoes are producing large amounts of CO2, and that caused an increase in climate, just like what's happening today by the increase in CO2. And that reached a peak in the Cretaceous around 85 to 90 million years ago, during a time called the Cretaceous thermal maximum. And temperatures there were 5 to 7 degrees higher than they are currently. So to put that into perspective, 5 to 7 degrees, currently, since 1900, temperatures have increased by around 1.2 degrees C. So the situation was much worse in the Cretaceous. And the Earth was very different and responded very differently to those temperatures. So there were hardly any ice packs, most of the ice had melted. Sea level was much higher, so most of the continents were covered by shallow seas. And we see evidence for those shallow seas within the rocks. We see abundant marine sediments, marine muds and limestones filled with things like this. And this is an ammonite. We're all familiar with ammonites. There were marine reptiles. So there were prolific, abundant oceans filled with life and a tropical environment. So the Cretaceous was a lot warmer than present. How did that affect life on Earth at the time? So one of the really surprising events that occurred at this time was the almost complete disappearance of coral reefs. Now, we're used to thinking of coral reefs as an indicator of the health of the oceans. And during the Cretaceous thermal maximum, corals disappear and reefs start to be formed by a new organism, by an organism called a rudist. And rudists they don't look it, but they're actually shellfish. They consist of a conical cone like the one pictured here, and the other valve is kind of a cap that seals that cone, with the rudist filter feeding out through the top. So corals stopped forming reefs and the rudists took over. And they did that because conditions became too challenging for corals. The rudists also evolved. There were many different types. So there were recliners that laid flat on the surface in areas of high current. So biological evolution occurred to allow the rudists to adapt to the conditions where the corals were no longer able to adapt enough to suit the environment. And what's important about this is it's marine organisms that have a really profound effect on the climate. Marine life is important for the climate because so many organisms in the oceans create shells or skeletons from carbonate minerals. And to do this, they take carbon dioxide from the water around them to build that carbonate. And organisms like plankton are particularly important because there's such a huge biomass. There are very large numbers of them. And when they die, their shells settle to the base of the ocean and accumulate as mud, eventually becoming rock, locking that carbonate, locking that CO2 away from the atmosphere. So marine life is like a pressure valve on the CO2 in the atmosphere. The more CO2 there is in the atmosphere, the more is absorbed by the ocean. The organisms take that CO2 out of the ocean, allowing even more CO2 to be absorbed. And so without marine life, it would be very difficult to control the carbon dioxide that's in the ocean. So we really need to be taking care of the oceans. The lesson that the Cretaceous tells us is that the oceans are crucial in the health of the climate. There are all sorts of controls on marine life, on the health of the oceans. So, for example, nutrients are really important. So those periods of Earth history where there are abundant nutrients entering the ocean, such as during glaciations, when there's significant weathering of material, of minerals, and those minerals are being transported in water to the ocean, they tend to be very, very nutrient rich, highly productive oceans. Times when there's large amounts of CO2 in the atmosphere, like in the Cretaceous, are really challenging for organisms because that CO2 dissolves in the ocean as carbonic acid. And it never actually makes the ocean acidic. The ocean is naturally alkaline, but it makes them less alkaline. It makes them more neutral. And that makes it difficult for organisms to grow carbonate. And some carbonate dissolves, so shells start dissolving. And this is a process known as ocean acidification. And that's currently occurring within our oceans. So the oceans have become 30% more acidic since 1900. And that's causing challenges for things like coral reefs. So we see evidence in coral bleaching events, killing off large amounts of coral. During the Cretaceous, what happened was the coral died off, it became really restricted, and the rudists took over. But what's crucial about that is that required biological evolution. And biological evolution is slow. It can't keep up with really rapid change. So to give you an idea just how slow evolution can be, this slide shows the evolution of these guys, of the ammonites that formed from creatures with straight shells. And that process of coiling, just simply coiling this shell and increasing the size of the organism, took around 30 million years. So biological evolution is relatively slow, and it finds it difficult to adapt creatures to rapidly changing conditions. And that, of course, is important because today CO2 is increasing in our atmosphere much faster than it did during the Cretaceous. So there have been periods of Earth history when environment has changed very quickly, too quickly for organisms to evolve and adapt to survive. And generally they are marked by mass extinctions. And that occurred at the end of the Cretaceous period 66 million years ago, with the disappearance of the dinosaurs, the ammonites, and around 45% of species on Earth. And this mass extinction was caused by the collision of an asteroid with the Earth. So that's an object like this. This is a meteorite, a rock from space, a piece of an asteroid. And yet that event was caused by the collision of an object 10 kilometers in diameter that produced an impact crater 170 kilometers across. Now, of course, that event is very different from what's happening today. So the impact probably had caused 6 months of very restricted light, possibly even darkness. There was the immediate effects of the impact that killed off a lot of really large creatures. And yet what it shows us is that biology, the biosphere, does not respond well to very rapid changes in environment. It's unable to adapt. And when we have the disappearance of large numbers of creatures, the natural world becomes less resilient. It becomes less capable of compensating for climate change. So that's a concern, because we are currently, some people say, in a mass extinction. Species are disappearing more quickly than at most times during Earth history. And actually, this is nothing new. Humans have always had this effect on animals. It started at the end of the last glaciation with the disappearance of most of the megafauna. We hunted them to extinction. And it's our other activities. It's the hunting, it's the habitat contraction as we take up more and more space for our cities and our farming that's causing the extinction of animals. And that's really important, because it's the living world that in part compensates for climate change. It helps control the CO2 in the atmosphere. Life is one of the reasons why our planet is so resilient against climate change. It acts as a pressure valve on the CO2 in the atmosphere. Of course, along with many other processes, but it's life that makes our planet different. So let's look at some of the other planets in our solar system and see if they can teach us anything about climate change. So Venus is nearly Earth's twin. It has roughly the same composition as the Earth, and it's roughly the same mass. It sits slightly more towards the sun, which means it's heated slightly more, and yet its surface conditions could not be more different to the Earth. It has a thick CO2 atmosphere and a surface temperature of an enormous 460 degrees. Venus couldn't be a more uninhabitable planet. And the question is, why is Venus like this? So models for the climate of early Venus suggest it was very much like the Earth. It may have had oceans up until around 2 billion years ago. What probably helped Venus is it rotates slowly in the opposite direction to the Earth. And that helps the formation of clouds, which caused a cooling effect on Venus. And the young sun was rather faint. And as the sun got hotter, so did the environment on Venus. The oceans started to evaporate. And once you start removing the oceans, that pressure valve on carbon dioxide in the atmosphere disappears. You can no longer dissolve CO2 into the ocean to remove it from the atmosphere and lock it away into rocks. And the water, the oceans on Venus, disappeared before there was any life, if there was any life at all on Venus. And as we've seen, living things help the atmosphere, help the climate compensate. On Venus, Venus experienced what's called a runaway greenhouse. The oceans evaporated and all control was lost of the carbon dioxide in the atmosphere. Now, this probably can't happen on Earth. Calculations have suggested that we'd have to burn 10 times the amount of all fossil fuels on Earth to cause a runaway greenhouse effect. And then it might not even happen. But Venus is a sobering tale about what happens when climate gets out of control. So the planet Mars couldn't be more different to Earth. It's a smaller planet than Earth and has a thin CO2 atmosphere. But early in its history, it probably had an environment much more like our planet, with oceans. So could we escape climate change by moving house, by moving to Mars? Well, that seems unlikely because currently the atmosphere on Mars has such a low pressure that on the surface, water boils. So people couldn't survive on Mars without pressure suits, without living indoors all the time. To change Mars' environment could take hundreds of thousands to millions of years, if we can do it at all. So escaping to Mars isn't really a possibility. There are other planets. Astronomers have been discovering planets around other stars, in excess of 4,000 planets to date, and some of those sit in the so-called Goldilocks zone, where liquid water could survive on the surface. Potentially, some of these planets could be habitable. Even our nearest star, Proxima Centauri, has a planet in the Goldilocks zone. So perhaps one of these could be Earth Mark II. And yet when we look at Proxima Centauri, we can see the problem. The planet there is locked in synchronous lock, like the moon. So one face always points towards the star, leading to really extreme weather. The star is also very active, dousing the surface with radiation. So we probably can't live on Proxima Centauri. Even if we could, getting there is a problem. With current technology, it could take 1,200 years to get from here to Proxima Centauri. The inescapable conclusion is that we have one home, one blue planet, and that there is nowhere else in the universe that we know of that can sustain us. So we really do need to take care of our home. It's our one chance of survival. So what will be the consequences of climate change? Well, that's fairly easy to predict because we're already seeing them. There will be more and more extreme weather events, causing damage and deaths around the world. There will be an increase in sea level, causing flooding and displacement of people. And those areas of the world that are already inhospitable will expand. There are already summer temperatures in some parts of the world that make it difficult for human beings to survive. This is all going to get worse as climate change continues. And looking back at the Earth's history, we've seen that it's the living world, it's the natural world, it's living things in the oceans that compensate for climatic change. We need to protect the living world. We need to protect our oceans. We need to protect habitats to ensure that those living things protect us. So is there any hope? Has climate change already gone on too far for us to do anything about it? Well, who would have thought a few years ago that most new cars on the road would be hybrids? Or that so much power would be generated from renewable sources rather than from fossil fuels? So there is positive change. There are things that we can all do at a personal level. Of course, one person changing their lifestyle does not have an enormous effect. 8 billion people changing their lifestyle does. It's the CO2 that's produced in our names that's driving climate change. We can Be responsible when it comes to choosing what we eat and what we buy and what we throw away, on how we travel. Even simple things like the temperature that we keep our homes. They will have an enormous impact on CO2 if we all do it. But perhaps the most important thing we can all do is to bear the environment in mind when we vote. Because it's our politicians, it's our governments that make policy, and it's policy that changes the world. And the low carbon economy is absolutely reliant on new technology, and that requires new resources. There's lithium and nickel and cobalt, neodymium, and the rare earths. Rather ironically, the mining industry is going to be part and parcel of saving the planet. We need those resources. Of course, we're currently in the most unprecedented global crisis. But there has been some positive signs, even in this really dark time. Because we have stopped doing what we usually do, pollution has fallen dramatically in cities across the planet. Even the waters of Venice have run clear for the first time. What it really shows us is that our world can recover if we give it the chance. Now let's remember, this is our home. This is the one blue planet that we have in the universe that we know of. If we take care of our planet will take care of us.